Hello class. So on this video, we're still on section 3.7. In the previous video, we talked about the solutions or types of solutions that we get when we have a spring mass system, right, where we include damping, right? So the first type of spring mass system we had no damping and free vibrations. And then the second one, which you saw in the previous videos, was where we had free vibrations still, but we allowed damping. And one of the things that we saw, which again, I didn't justify, and you don't have to worry about the justification, is that the damping forces acting on an object are proportional to a power of the instantaneous velocity, right? And we just assumed that it was the first power, right? So in particular for us, the damping forces were equal to beta times dx dt, right? That's instantaneous velocity. It's the derivative of x with respect to time. Where we required beta to be greater than 0, again, in this case, since the explanation as to where these forces come from or where this assumption comes from is not very easy, I require beta to be greater than 0. For the Hooke's law, the Hooke's law proportionality constant k, it was easier to explain why k ended up always being greater than 0, even though we didn't give it a sign, right? So we didn't assume that it was, we'll just define k. For beta, it's not that easy. So again, I'm just going to assume that it's greater than 0, and then you just take it as a fact, right? That beta is always going to be greater than 0 for our purposes. So that was the idea, right? So now we had a second order, again, linear, constant coefficients, homogeneous ODE, right? So we had 3 types of solutions, right? Because the 3 types that we got were equivalent to the 3 cases that we saw from before, right? Because we have a characteristic polynomial of degree 2, we have 3 different cases that we can get for the roots, right? And the first case was when we had 2 distinct real roots, right? And there were a lot of equivalent ways to look at it in terms of the string mass system, or 2 specific ways to look at it. One was having 2 real distinct roots was equivalent for the system being overdamped, right? Meaning that beta was too large and was causing the oscillations to go, well, basically to disappear, right? So no oscillations were happening because our solutions were just going to 0 very fast. In terms of beta and k, right, our damping constant and our restoration force constant, us having overdampedness or having 2 distinct real roots was equivalent to beta squared over 4m being greater than k. And I did all that in the previous video, so I'm just reviewing it. Right, so what I did here is I went over this case, right, and I choose a beta and a k, and a mass I just choose 0.5 at random, but specifically I chose beta and k so that beta squared over 4m is greater than k, right? So we're in this case where we have 2 real distinct roots. And I plotted a solution, right? And then you see what's going on, that we don't get oscillations. In fact, it starts at 2, because I gave it an initial condition for position, starting at 0, that at t equals 0, we're at positive 2. I also gave it an initial condition of 0 initial velocity, meaning that you just let go of the object instead of giving it a push or pull. You can see that immediately or really quick, we start approaching 0. And you can see that from the solution, right? If you look at this thing here, when you multiply e to the negative 4x out, we get exponentials with negative exponents. Right? And as we know that it's approaching 0 as x, in this case, or in our purposes t, gets very large. Now, in the case in which we're critically damped, in terms of the roots of the characteristic polynomial, this was equivalent to the case where we had 1 real root with multiplicity 2. And then in terms of the spring mass system, it meant that it was critically damped, meaning that beta was chosen specifically so that if beta was any smaller, right, and usually you'll have, beta will be changing, right, because you'll have beta squared over 4m, so m is usually going to be fixed, so you could switch beta, or you could change beta, right? But anyways, beta was chosen or was given so that if beta were anything smaller, we would have a system with 2 complex roots, so no real roots. And because of that, we said that the system was critically damped. Right? So it was at that critical point where beta is perfect enough so that if it's any smaller, you would have 2 complex roots, right? But it's in the point where you get equality. Right? And equality meaning that in terms of what we were talking about before, that lambda squared was equal to w squared. Right? If you remember, that was what was inside the square root. Right? If we wrote it in terms of lambda and w instead of beta, k, and m. If we write it in terms of beta, k, and m, this is equivalent to beta squared over 4m being equal to k. So as we know, if we look at the solution, and I'm using the same, so I chose beta and k, right? So that I have equality of beta squared over 4m being equal to k. And then I gave the same initial conditions, so start at a position of 2, and then initial velocity of 0. And then I plotted the solution, and again, you see that we get no oscillation. We're going to 0 very fast. It's not the same, right? Because now we have, if you remember what the solution looks like, it's an exponential. Still, it's going to have negative exponent here, so -2. But the other factor, we have a factor of x multiplying. So that changes things a little bit. For example, you can see here, it's a little bit hard to see, but we're actually below the x-axis. Right? While here, we're always above the x-axis. Right? So the fact that we have an x there changes things a little bit. But still, we don't get oscillations. Then the last case, underdamped, meaning that beta was small enough that the damping forces weren't too large, and then which allowed the system to have oscillations. Right? This was our case 3, which in terms of the roots was the case of 2 complex roots, right? 2 distinct complex roots. And then in terms of beta, k, and m, it was equivalent to beta squared over 4m being less than k. So in this case, 2 complex roots, we know that we get sine and cosine terms. So in this case, we do get oscillations. And again, in the form that the solution is written, it's not very easy to see what the amplitude is. Right? So you can see that it's not very easy to see what the amplitude of cosine and sine is. But we do get oscillations because we have the cosine and sine functions here, which we know are periodic and have an amplitude. So in terms of our solutions, right, those are the 3 cases. Right? And I'm just plotting here so you see the difference, right? In the first 2, we don't get oscillations, but in the third one, we do get oscillations. And that corresponds to the damping forces not being too large, so they're small enough that the system does allow for some oscillation to happen. So I just wanted to show you a couple plots of this just so you can see visually what's happening with the solutions. Right? So that's going to be it for this video. Right? In the next video, we're going to do an example of just a system that has damping, and then we're going to talk a little bit about forces that force oscillations on the system. So when we don't have free vibrations.